So here we go. We're going to start off today's notes with an example of what we've been doing. We're going to solve a system by graphing. So why don't you pause the video and graph these two lines and find the point of intersection. So what we should do, y-intercept of 1, slope of 2/3, so up 2 over 3, up 2 over 3, up 2 over 3, and going the other direction also to give ourselves a nice straight line, of course. And we get this line for the red. And then the green line, we have a y-intercept of 4, and we're going down 3 over 1. Down 3 over 1, down 3 over 1, other way also. And we get that line. And if you compare this to what we've been doing, what we see here is we don't really intersect at a nice crossing of grid lines like we have with all those other graphing problems. And that makes it difficult to pinpoint what's this ordered pair right here. It's some sort of fractional value. We did the graph right, but we don't really know. I mean, we don't know what this point of intersection is. And that's what today is going to be all about. It's going to be about how can we effectively deal with solving systems in an algebraic way, in a way that we don't have to rely on drawing a graph. Okay, so let's work through this. I'll talk you through it, and then we'll kind of formalize the process that we're going to use upon completing this problem. So what do we know? Well, we know that y is equal to this, and we also know that y is equal to that. So if y equals both of those things, shouldn't those two things equal each other? I hope you see the logic in that. So we can do 2/3 x plus 1 equals negative 3x plus 4. And at this point, I hope you can kind of see where I'm going. Now we have an equation that has x's on both sides, but only x's, and we can now solve this for x. So we need to get everything together. We need to get everything on one side. I'm going to add 3x to both sides. And at this point, there's lots of different ways that you can go about solving this. And in order to add this, I'm going to need a common denominator. So 3x is the same as 9/3 x. I'm doing that because now I can add these x terms together. And I get 11/3 x plus 1 equals 4. Subtract the 1. We get 11/3 x is equal to 3. And now to undo multiplying by this fraction, I'm going to multiply both sides by the reciprocal of that fraction. Which is 3/11. So those cancel. We've got 3 over 1 times 3/11. X is equal to 9 over 11. And now that we have that, we can take that thing, and we know how x and y are related to each other. We can substitute it into either one of these. And you know what? Since the second one doesn't have fractions, I'm going to substitute it there. It seems like it's going to be slightly less work. So y is equal to negative 3 times 9/11 plus 4. And now we just number crunch. This is negative 27 over 11 plus, okay, 4. We're going to need a common denominator here. I'm doing this without a calculator. 4 is the same thing as 44 over 11. And now that I have that common denominator, I can add these together. And what we get is 17 over 11. So the place that these two lines intersect is the ordered pair 9/11, comma 17/11. That's a difficult solution to get exactly from a graph. So went through it, great, but what exactly did I do? Let's summarize this on the next screen. the substitution method. This is called the substitution method because we are substituting things for other things. And what we're doing, step one, is that we solve one equation for one variable. And that step was done for us in this last problem. The equation's already said y equals, but we need to get that one equation so that a variable is all by itself. And then once we have that, we're going to substitute that expression into the other equation. It's important you put it into the other equation. And we're going to solve for the remaining variable. That part we did. We took one equation, one expression, one side of the equation, substituted it into the other one for y, and then we solved for the remaining variable. And once we had that remaining variable, once we found that value, we're going to take that value from step number 2 and we're going to substitute it into step 1, that thing that we had where the variable is alone, and we're going to solve. So 3 steps. And we're going to go through 2 examples that shows how to use these 3 steps nice and quickly. So here we go. Y equals 3x and y plus x equals negative 32. Okay, so step 1 was to solve one equation for one variable. And that happens to be done already. We have y equals 3x. And don't worry, in the next example we'll do one where step 1 isn't done for us. Step 2 is we take that expression, this, and we substitute it into the other equation, so into the second equation. And we're going to substitute this expression here in for what it's equal to. So what equals 3x? The y equals 3x. So what I'm going to do is I'm going to take that second equation, and I'm going to write, where the y was, I put parentheses, plus x equals negative 32. And what do I put there? I'm putting 3x. And now we have an equation that we can solve. We have 4x equals negative 32. Divide by 4. X is negative 8. So that's the end of step 2. We substituted the expression from step 1 into the other equation, and we solved. Now step 3 says we take that value from step 2 and we substitute it back into step 1. So y equals 3 times negative 8. So y is equal to negative 24. Done. X is negative 8, y is negative 24. We just figured out that these 2 lines would intersect at negative 8, negative 24. Solving systems algebraically is a much more efficient way to solve over graphing. It's a far better method. It will always work regardless of what the numbers are. Second example, we're going to use the substitution method again. And in this one, step 1 is not done for us. So we're going to have to do it. And step 1, there's a lot of different choices because when you look at these equations, there's 1, 2, 3, 4 variables. What we have to do is we have to pick one of these 2 equations and pick a variable, and we need to solve for that variable. And it doesn't really matter which one you use, except there's oftentimes a more efficient, there's a better choice than others. And what we're looking for is an easy way to get a variable alone. And if you look at the second equation, one of those 2 variables is going to be quicker to get alone than the other, and that variable is the y. Anytime you see a variable without a coefficient, that's real easy to isolate because we take the other term and bump it to the other side. If we had picked the top equation to solve for a variable, we could move the x to the other side and then get rid of the 2 steps. Or we could move the y term to the other side and divide by negative 6. Again, 2 steps. But I'm going to choose the second equation, y minus 3x equals negative 13, and I'm going to solve it for y. And that's my choice. You can choose something else if you want, but doing it this way, you're oftentimes going to avoid having to deal with fractions, which removes potential places to make mistakes. So there's the end of step 1. I have just picked one equation, and I have solved for one variable. Now step 2 says to take that expression and substitute it into the other equation. So for step 2, I'm going to write down the other equation, but in place of the variable that I just solved for, I'm going to put empty parentheses. And these empty parentheses will help to avoid mistakes when I do my substitution. So I'm taking that expression from step 1, and I'm substituting it into the other equation here. And now I have an equation with one variable. This I can solve. (6x minus 6x), that's 0. I'm left with negative 26 equals negative 11. And gosh, there's no more x's. What do we do? Well, if you remember from the graphing, there's 3 things that can happen when we solve a system of linear equations. We could get one solution, which we saw in the previous example, or we can get no solutions, or infinite solutions. This is a symbol for infinity, and SOL, an abbreviation for solutions. So which one do you think it is here? Pause and answer the question, please. And what you have to think about at this point is this statement true? Can negative 26 equal negative 11? And I hope you're all saying that no, that can't be true, which means there is no value for x and y that will make that true. In this situation, when the variables completely disappear and you're left with a false statement, there is no solution, which means if we had gone back to the original equations, we would see that they're actually parallel lines. If in your solving, your algebraic work, you get a statement of equality where all the variables go away after your substitution, and you end up with something like 5 equals 5, or 0 equals 0, that would be a case where it's infinite solutions, because it doesn't matter what x and y are, 5 will always equal 5. 0 will always equal 0. And that's one of these instances where we're actually looking at coincident lines, meaning they're the same line in reality. So this is where I shall leave you. This is something that we're going to do some practice with. With some practice, I hope that you start to see that this is becoming the same kind of equations that we've been solving for quite some time after you do that initial substitution.